yesterday we had started with this hydrogen atom problem, and we have basically derived what is the form of Schrodinger equation and how we can solve it. Okay. There actually what we have done till date is we have got the angular part, and I think this theta and phi parts we have separated. And for the phi part, we know the solution is obvious, which is e to the power im phi. And for the theta part, we saw that this solution will be our associated Legendre polynomial. Okay, so that's what we have seen, and this reason is that the form of the theta equation it is similar to that of Legendre differential equation. Okay. So we have actually seen that this equation number 15 is the particular form of equation, which is basically the expression that is coming for the theta part, and then the solution will be basically this Lth order associated Legendre polynomial, that is PLM. Okay, and then we have actually discussed that how these things can be derived. So this is the general expression, that is equation number 18. Okay. That is PLX will be 1 over 2 to the power L times L factorial, and then ddx to the power L x square minus 1 to the power L. And from there you can actually get all the Legendre polynomials. Once you have the Legendre polynomial, then you can get the associated Legendre polynomials also. Okay. So if any of you is interested, then you can basically plot these functions like Px as function of x, and then you can see what is the functional dependence of different orders of these things, because these things will be directly related to the actual wave function that will constitute the equation. Okay. And after that, what we did is we looked at that how basically what is the relation between L and M. So we have seen that for a given value of L, there are 12 plus 1 values of M that are possible. Okay, so this L is something which we call it as azimuthal quantum number, and M is called as magnetic quantum number. Okay, so let's say if L is 0, that means the values of M that are possible will be minus L to plus L, that means 0 itself. Now, if L is 1, then the M value that are possible will be minus 1, 0, and 1. Okay. Similarly, for L equal to 2, it will be 2, 1, 0, minus 1, minus 2. Okay, so it will go like that, which means that for a particular value of L, there will be 12 plus 1 level degeneracy that is present, which is described by the magnetic quantum number M. Okay. So if you remember that this L and M we have introduced by hand in order to get the solution, but in principle these quantities correspond to something which is related to the energy eigenstates and also the actual wave function, that is the quantum number which describes the system. Okay. Okay, so I think up to that is done. So today we'll look at basically how we can proceed further with this. So the first thing that we'll do is that we will try to find out the coefficient of this expression. So if you know that we are kind of trying to find out the solution, so we know one solution is basically PLM, and other is this e to the power im phi. So this is theta and phi part. So these two constitute this total basically assume this angular part of the function, that is YLM. Okay. Now we want to know what is the coefficient. So the only way to do this is basically we have to normalize the wave function. Okay. So how we'll do it? So we'll consider a small volume element. Okay. Am I audible? Hello.
Yes, sir.
Okay.
Yes, sir.
So we'll consider a small volume element dq bar in this theta r theta phi plane. Okay. So this volume element will be r square sin theta dr d theta d phi. So I hope everyone knows how to get this volume element. Everyone knows? Is it?
Yes, sir.
You know it,
Yes,
right?
sir.
Okay. Good. Okay. So basically it is nothing other than small volume that is present between r to r plus dr and theta to theta plus d theta and phi to phi plus d phi. Okay. So now what we will do is that we will take the psi square and we will integrate over this small volume element, and that integration limit will be over the entire volume of the phase space. And as per basically normalization condition, this has to be equated to 1. Okay, so here you see this psi square will be a product of r square and y square. So r square will take this small r square dr in the integral, and for y square it will be theta and phi part. Okay, so now if we do that, so for radial part the integration limit will be 0 to infinity because it cannot be less than 0. Otherwise basically electrons will end up has to collapse, and basically it's unphysical limit. Okay, and infinity is the maximum limit. And for theta and phi, it has some symmetry, so the boundary condition will be governed by that. So it will run between 0 to pi for theta, and for phi it will be 0 to 2 pi. Okay. So if we do that, use this normalization condition, then finally we will find this particular expression. So this is the coefficient which you see here, that is minus 1 to the power m. In the bracket, it is 12 plus 1 divided by 4 pi, L minus m factorial divided by L plus 1 m factorial. And these other two are basically the functions which we got earlier, that is e to the power im phi times plm cos theta. Okay, so this is the total angular part of the wave function that we'll get here. So you see that this he is already having the coefficient which we got from the normalization condition. Okay, so this particular function ylm, this is called as spherical harmonics. Okay, so in anywhere if you get a question that what is spherical harmonics, I hope you can answer. Okay, so is it clear?
Yes,
no answer, sir. So I'm getting it is clear. Okay, so spherical harmonics means it's only takes care of the angular part. Okay, so now you need to keep something in mind, or that you see we have started with the Schrodinger equation which has r, theta and phi, right? And we have basically used separation of variables technique, and from there we have got the basically different equations, and then at this point we have arrived at the exact expression for this angular part of the wave function. Okay, so now what is the catch here? The beauty of this problem is that so far we have not even looked at what will be the form of the potential. Okay, so we have got the exact form of ylm without even having any knowledge of what will be the form of potential, whether it is 1 over r or 1 over r square or 1 over r to the power 1.5. Okay, you understood what I'm saying? So what does that tell us? Anyone?
so that the potential is not dependent on angular parts.
So who is this?
Roshan.
Roshan. So you are saying potential is not dependent on angular part.
Yes, sir.
So is that the message you got from here?
Sir, until now we haven't talked about potential, so I think that's what it is trying to say.
So why do you think a potential has to be dependent on the angular part?
I don't know.
I just think it's okay. I mean, it's not like a interview is going on. Just tell me, why do you think the potential has to be dependent on the angular part of the wave function?
No, sir, I did not consider the potential to be dependent on angular part.
Okay.
Yeah.
Okay, so let's just think about this. That you are solving a Schrodinger equation, okay? Right? Any Schrodinger equation, right? So what is the first thing that you do? Roshan, can you hear me?
Yes, sir.
So tell me, suppose I give you a any quantum mechanical problem, you have to solve the Schrodinger equation. So what will you do?
So first I take the wave function and
No, tell me
also the
step by
potential.
step. Tell me step by step what you will do.
So for this Schrodinger equation, right?
Yes.
Hello.
Hello.
Yes,
Yes.
sir. So I take a wave function and also a potential. So
You take your wave function and also the potential.
no, sir. Actually, if we take this time independent Schrodinger equation, we only need to know the Hamiltonian and the wave function.
So
Yes,
the
sir.
question here is that, okay, this is not only specific for Roshan but for any one. Okay, let's see. the question here is that I give you a quantum mechanical system. Okay. You have to solve the problem. So what will you do? Tell me step by step.
So firstly, I think we have to identify the Hamiltonian.
Okay. So first step you are saying Hamiltonian. Okay. Then.
So then apply a time independent Spherical equation and then find the wave function.
So what is this Hamiltonian exactly?
So it's kinetic term plus potential term.
Okay. So it is Ke plus P. What is this kinetic energy term?
It's minus h cot square by 2m del square.
Okay. So let's say something of the order of del square. What is the potential energy term?
So it depends upon the system, sir.
Good. Very good. Okay. Next, what you do?
So then we apply this time independent Spherical equation and then find the wave function.
So what will you do then? So how will you find out the function?
So by applying time independent Spherical equation.
Okay. So you solve it, right?
Yes, sir.
Okay. And then you find psi. Okay. Right. Okay. So now tell me which one comes first and which one comes second. You have this and that. Which is coming first and which is coming second?
So this potential energy is coming first.
Okay. So which one affects which one?
So potential energy affects this wave function.
These are all operators or functions. Okay. Okay. But anyway, it's okay. I understood the thing. Okay. So this part, it affects this one, right? Because you are first starting with this quantity. Okay. So Roshan.
Yes, sir.
So now you understood. You said the wave function is affecting the potential, or independent,
Yes.
basically, yeah, independent,
Yes,
something
sir.
like that. So wave function is a result of the potential which is governing the system.
Yes, sir.
Okay. So this is the end product. So it cannot affect the potential. Potential, on the other hand, it affects the wave function. So I hope this concept is clear to everyone, right?
Yes, sir.
Okay. So now here in this case, we have, let's say, RR times YLM theta phi, right? Okay. And what we have seen that we got an exact expression okay of this second part, right, without having any knowledge of VR, right? So my question is, what does that tells you? Anyone? Anyone?
So does it mean that for any spherically symmetric potential, we will be having this spherical harmonics in our wave function?
Right. Can you go a little bit into details of this?
So for this spherically symmetric potentials, we do not have that angular dependence upon potential energy. So therefore, every system will be having this spherical harmonics in its wave function.
Yes, so this is partly true. So the exact information is that as long as the system has spherical symmetry, it's not actually the system. Okay, it's the potential. As long as the potential has spherical symmetry and it is only dependent on R. Okay, you understood? So it means that it's a central force. Okay, then you will always get this solution as the angular part. So it will not change if the functional form of VR changes. So as long as system has this spherical symmetry, or basically not system, but the potential has this spherical symmetry, or let's say it is a central potential. Okay, understood? You will always get the solution. Is it clear? So,
Yes, sir.
so the potential can be 1 over r, it can be 1 over r square, it can be, let's say, 1 over r cube, it could be r square, it could be r to the power 5, anything. But at the end, the angular part will not be affected by this. Okay, right? So now this is a trick question, that in any exam, if the potential expression is not given and still you are asked to write down the azimuthal part, or let's say the angular part of the wave function, what will be the answer? So it will be this wave function basically. Okay, as long as the potential is a function of r and it's in a spherical, basically it's kind of that, then it will always be the solution. So you don't need to solve the problem. Okay, so if somebody tells you what will be the solution, angular part of the solution for m equal to 0, l equal to 1, all you need to do, you plug in those numbers and you get the values. Okay, is it clear?
Yes, sir.
Okay,
Yes, sir.
chalo. So now we will see how are these spherical harmonics looking like. Okay, so here basically we have so if we put different values of L and M, then we'll get y00, y10. So this y00 is square root of 1 over 4 pi, and this one is, I think, some coefficient times cos theta, it will be sin theta. And as long as m is 0, you will not get any pi part, but when m becomes non-zero, then you will start getting e to the power I, e to the power this I phi or 2I phi, something like that. Okay. So these are basically very simple way of calculating this. And as I said, that y theta phi is same for all spherically symmetric potential, but it affects the regular part, sorry, radial part. Okay. Okay. So now, so we have got the solution for the angular part. Now we'll look at the radial equation. Okay. So you remember that when we equate basically both sides to this coefficient L times L plus 1, then we ended up with this equation. Okay. That is ddr of r square times d capital R d small r minus 2m r square by h bar square vr minus e times r will be L times L plus 1 times r. Okay. So this capital R is basically the radial wave function. Okay. Now, if we want to solve this, what we will do is that we will consider a change of variables. So we will consider a new variable, that is u, which is also a function of r, as a product of small r times capital R. Okay. And then we'll take the derivatives of du, dr, and dr, basically first order, second order derivative of both sides. Okay, so because r is u divided by small r, so we can get the first derivative and second derivatives. And with that, what we can have is that we can replace, or we can substitute capital R with u in this equation. Okay, so basically our equation number 23, it basically changes to a form which is in the form of d2u dr square. Okay. And if you look at this expression in equation number 23, then you see we have minus h cross square by 2m d2u dr square, which is basically, let's say, the kinetic energy term. And within the bracket, we have v plus h cross square by 2m times L plus 1 divided by r square times u, which is equivalent to the potential energy term. Okay, on the right hand side, we have E times u. Okay. So you can see in this blue colored option, we have written that minus this equivalence I have mentioned here. So here, this term within the bracket, it looks similar to that of an potential. Is this clear so far? Okay.
Yes, sir.
So now what does that tell us? So here basically all we can say is that we have two terms in the potential, and we are kind of like writing it as V effective, which is basically a sum of V plus h cross square by 2m times L plus 1 by r square. Now this V is nothing other than the Coulomb potential. If you remember, that is the attractive potential between electron and nucleus. Okay, but here we are getting an additional term, okay, which is 1 over r square. So we call it as centrifugal term. Okay, why? Because usually in centrifugal force problem we get this kind of term. So that is why we name it as centrifugal term. Okay. So now what we will do is that we will use first the normalization condition, which means that this u square dr will integrate over the entire volume of r, and that has to be equal to 1. Okay. So we can do that, but if we want to process further, then we need to have the exact form of the potential, because here actually V is there. So without having knowledge of this, we cannot do this. Okay. So let us see how we can do further. Okay. So for actually hydrogen atom problem, we know that basically, as I said earlier, that we have a nucleus and an electron, and nucleus is heavier than the electron. So we can say that it's a heavy nucleus and light electron problem. Okay, and the potential of let's say the between these two the electron and the nucleus will be minus c square divided by 4 pi epsilon naught times 1 by r. So this negative sign tells that it's an attractive potential. Okay. So if we plug in this Vr into the equation earlier, then we get this expression, that is this kinetic energy term, and within the bracket we have this 1 over r term and 1 over r square term. Okay. So this is pretty straightforward. Okay. So now what do we have? So actually here this potential has been plotted as function of radial distance. Okay, so here you can see this effective potential is a sum of two different terms. So we have a repulsive term that goes as 1 over r square, and we have an attractive force, that is potential, that is 1 over r. It varies with that. Okay, so this first term is centripetal potential. So here actually you can see, if I just plot this centripetal potential, then I get this yellow line, which is let's say a typical 1 over r square dependence. Okay, so as we go close to r equal to 0, it will diverge. Okay, so it will have an asymptotic kind of like increase close to r equal to 0 value or axis. Okay, now the Coulombic force, if you plot it, this is the blue line. It is an attractive force, which means that the potential will be negative. So here also it is negative and it diverges as we go close to 0. Okay, so at r equal to 0, we don't have an exact solution because both the terms diverge. Okay. However, if we add these two terms, which means that the combined contribution of this centripetal force and the Coulombic potential will have a dependence which looks something like this red colored graph. Okay, so we see it also diverges close to 0, but it has one additional property, that is that it has a minimum. Okay, so which means that any particle or system that is governed by this potential will have an equilibrium position, or let's say energy minimum, and then the basically as we go higher at higher values of r, then this potential will kind of like increase slightly, and it will reach almost a constant value. Okay, and at smaller values of r, it will diverge. Okay, so as it says that unless L equal to 0 case, the centripetal force is dominant, because if L equal to 0, this first term will be absent. So it is only the Coulombic potential. Okay. So now if you remember that what is L equal to 0, that means it is almost like kind of S-wave system, you can say. Okay. But if L is non-zero, then we have basically all these PDA orbitals, and then basically for them we have to have this kind of like V effective, which means that the potential will have a minimum. Okay, so that is the kind of like behavior of this potential at different values of r. Okay, so any question on this? No? Okay, good. Okay. Okay, so now if you want to solve further, so we ended up here. Basically, we have this equation here, that is d2u dr square and 1 over r square within the bracket. Okay, and u in the right hand side. So that if we want to do, then what we have to do is that we want to solve it, so what we do is that we consider a kind of replacement of variables. So I will use k equals to minus square root of 2me divided by h square. Okay. So for a bound state, we know that energy has to be negative. So if E is less than 0, then k has to be here. Okay. So now if I divide both sides by E, then what I will have is I can write this equation as 1 by k square times d2u dr square will be equal to 1 minus m square divided by 2 pi epsilon naught h bar square kappa times 1 divided by kr plus L times L plus 1 by kr whole square times u. Okay. So at this stage, I will do one more change of variables. So there's a new variable rho, which is a product of k and r. Okay. So k is independent of r because it's only a function of energy and r. Okay. And rho 0 is defined as this coefficient, that is m square divided by 2 pi epsilon naught h bar square by k, which is basically this particular term. Okay. So now if I do this substitution, then this equation will change to this form, that is d2u d rho square will be 1 minus rho 0 divided by rho plus L times L plus 1 divided by rho square times u. Okay. So this is basically a very simple expression which it looks for this radial part. Okay. So we have done several change of variables at this stage. Okay. So now we will look at what is the asymptotic behavior of this particular equation. So let's say if rho goes to infinity. Okay. So in that case, what happens is that let's say if rho goes to infinity, then this second term and third term, they will be almost negligible or absent. So we can ignore them compared to the first term. Okay. So in that case, d2 d rho square will be only u. Okay. So that is what we have written here. Now for such an equation, the general solution we know will be a sum of e to the power minus rho times e to the power plus rho, and we will have two coefficients. Okay, unknown coefficients. Okay. Now we will look at the boundary conditions. So as we know that if rho goes to infinity, which means that we are going far away from the nucleus. Okay, which is, let's say, an unrealistic scenario. So in that case, it is unlikely that we will find a solution. Okay, which means that this particular coefficient is 0. So we put b equal to 0 in this equation, in this expression. Okay. So the only feasible solution that we have is a to the power minus, a times e to the power minus rho. Okay. So we have this. Now let's say we will again look at the case when rho goes to 0. So earlier we looked at when rho goes to infinity. Now we look at the other opposite extreme, that is rho goes to 0. If we have that, then we can take this double derivative of this, and then what we will get is that d2u d rho square will be L times L plus 1 divided by rho square times u. Why? Again here, let us see here. Okay. So if rho goes to, let's say, what is happening here? Rho goes to 0. Okay. So in that case, basically, so we have basically two terms. Okay. So basically rho 0 divided by rho and L times L plus 1 divided by rho square. Okay. However, if you look at basically, so L times L plus 1 divided by rho square. Okay. So now if you look at basically, if rho is becoming smaller and smaller, then 1 by rho is basically becoming higher and higher. Okay. But 1 by rho square even goes higher than 1 over rho. Okay. Which means that if rho is very small, then this third term will be more dominant than this other term. Okay. So these other terms can be completely ignored in this limit. Okay. So that is why we have only considered this term L times L plus 1 divided by rho square. Okay. Only except of course L equal to 0 case, because in this case this will be 0. Okay. So if we have this, then what we can write here is that the general solution again. So here again it is basically d2 d rho square will be 1 by rho square. Okay. Solution will be equal to, the general solution can be written in this form, that is c times rho to the power L plus 1 plus d times rho to the power minus L. Okay. Now if rho goes to 0, then this term will be again very high. But this is again an unlikely solution, because if rho goes to 0, that means the electron will basically be present on the nucleus. So that means that the system will be destroyed, right? Because electron and nucleus, if the electron goes to nucleus, there will not be any atom, which means that it is not again a physical solution. Okay, so we will ignore this term, which means that we will put the coefficient to 0. So the solution for small value of rho will be C times rho to the power L plus 1. Okay, is this part clear? Any question on this? Hello.
Hello.
Mm-hmm.
Sir, just not clear. Once again, explain D part.
D part. Okay.
Yeah.
So let's say if I go close to rho equal to 0, so remember rho equals k times r, right? So rho goes to 0 means r goes to 0, radius goes to 0, right? So which means that the distance between electron and nucleus are almost basically absent, which means that electron is present on the nucleus itself. In that case, what will happen? The atom structure will not be existing, right? So it will be annihilation of the atom. So that is not a physical solution. Okay.
Yes, sir.
Which means that this particular term should not be there. And how will you ensure this? By putting the coefficient to 0. Okay.
Yes, sir.
Okay. Any other question? Anyone? No? Okay. So is it clear to everyone?
Yes, sir.
Okay. Okay.
Yes,
So
sir.
now further, so what we have got here, see, we have got basically two different forms. Okay. So one is, so basically we got two asymptotic forms. So one is rho goes to infinity, right? So that is far away from the nucleus. Okay. So we have seen in that limit the wave function will be only e to the power minus rho. That is the functional dependence, right? And if we go close to the nucleus, then the dependence will be rho times L to the power 1. Okay, right? So now from this knowledge, what we can do is that we can write down this wave function in this particular form, that is a product of those two terms, two asymptotic terms, that e to the power minus rho and rho to the power L plus 1. And there will be another function which will also be present, that will be v rho. Okay, so we don't know this, but we'll try to find out the expression for this. Okay, so u rho we can write it as a product of these three terms. Okay, right? So still now basically we are just looking at the boundary conditions and limits. Okay, so now with this, what we do is that we will look at the radial equation. So we have the expression earlier, and then if we take the first derivative of this, then we will get this particular expression, that is rho to the power L times e to the power minus rho, and within the bracket we will have L plus 1 minus rho times v plus rho times dv d rho. Okay, and we can take the second derivative and we will get this expression, which is in equation number 40. Okay, now with this, what you can do is that okay, so you see, like here basically you need to solve these things at your home. Okay, because these are quite long steps. Okay, so please solve it at your side. Okay, so now if we plug in these numbers, and then we can have these equations, of course. Now let's say if we want to, so we still don't know what will be the form of v rho. Okay, so one way of looking at it, basically we'll assume some particular form. So the easiest one will be a power series of rho. Okay, why power series? Because we have seen here that here actually we have rho times L plus 1 and then e to the power minus rho. So both are basically power series components. Okay, so here we will express it V rho equal will be sum over j equal to 0 to infinity a j times rho to the power j. Okay, what is j? So j is basically dummy indices here, and it will run from 0 to infinity. Okay, so this is a series expansion. Okay, now all you have to do is that you have to find out the coefficient, that is a0, a1, a2, and all these things. Okay. Okay. So now we will determine okay, so we will determine the coefficient, that is a0, a1, and all these things. So we'll take the first derivative. Okay, dv d rho. So if we do that, then basically it will be j times aj and rho to the power j minus 1. Okay. Now I can simply rewrite this as j plus 1 times aj plus 1 times rho to the power j. Okay. Why I am doing it? Because this j is a dummy indices. Okay, which means that I am summing over j equal to 0 to infinity. So if I replace j by any other term, let's say j plus 1, then also I will get the same solution, because it is just a power series. Okay, so that is why I can also write it in this particular form, that is a j plus 1 times a j plus 1 times rho to the power j. Okay, next what we will do is that we will look at the second derivative, and that will come up to be j times j plus 1 times a j plus 1 times rho to the power j minus 1. Okay. Now in equation 40, which means here actually, so this equation, what we'll do is that we'll put v rho. Okay. So we have d2v d rho square and dv d rho. If we put all this thing, then we get this equation. Okay, that is rho times d2v d rho square plus 2 times L plus 1 minus rho dv d rho plus rho 0 minus 2L plus 1, 2 times L plus 1 times V will be equal to 0. Okay. So one thing to keep in mind, that this V is small v. Okay, it is not the potential. That was capital V, and we have already took the expression for that. Okay. Now we have the expression for d2v d rho square and dv d rho. So if we put it in this expression, then we get these terms in series, and that is basically equation number 45. If we have that, then what we will do is that we will equate the coefficient of powers, which are basically equal powers. Let's say power of rho kind of rho square, things like that. Okay. So if we do that, then basically we will get one expression like this: j times j plus 1 times a j plus 1 plus 2 times L plus 1 j plus 1 a j plus 1 minus this is 6. And from this expression, I can express a j plus 1 in terms of a j. What is the connection between a j plus 1 and a j? So it's basically lifting, let's say j to j plus 1, or basically, let's say if I have polynomial series expansion, then I have first term, second term. So the first coefficient will be aj, second coefficient will be aj plus 1. So it is basically, if I know aj, then I can get aj plus 1. Now when I know aj plus 1, I can get aj plus 2. Okay. So basically this expression will help me to get values of all the coefficients. Okay. So this is called as recursion relation. Okay. So now what I'll do is that I will assume that a0, which is the lowest order term, is equal to a, capital A, and from there I will get the values of higher order coefficients. Okay. Okay. So here what I can do is that, again I will take some kind of like asymptotic limits. So let's say if the value of j is large. Okay. So let's look at if the value of j is large here. Okay, so in this expression, we are putting the value of j to be very large. In such case, what will happen is that this expression will take this form. That is, a j plus 1 will be 2j divided by j times j plus 1 times aj, or 2 divided by j plus 1 times aj. Okay, So in very simple way, as I said that A0 is A, so I can write AJ will be 2 to the power j divided by j factorial times A. So you just practice at home, you will see how it is coming. Okay, so it's like A2 will be something by A1, A3 will be something times A2. So this 2 will be multiplied by that many times. So that is why this 2 to the power j is coming. Okay, so now if I want to know that there is an exact result, okay, if I want to know the exact form of the solution, then what I'll do is that I'll write this AJ into the, I'll put this values of AJ into the expression for 0, and I'll get this particular form, that is A times j equal to 0 to infinity 2 to the power j divided by j factorial times rho to the power j. Okay, and this will give me A times e to the power 2 rho. Okay, or I can also write u rho, which is r times v rho, will be basically A times rho to the power l plus 1 times e to the power rho. Okay. Okay, so now before proceeding this, just tell me if this part is clear up to this. Clear to you? I have gone actually several steps ahead. Anyone has any question? So up to this, I think you have asked some question, but from here onwards, is there any question?
Sir,
Tell me.
sir, in equation 38, why did we multiply the two solutions of u rho?
Okay, very good question. Okay, you see, what we are doing is that we see for the case of angular part, we luckily got the solutions without even solving anything, right? Because we did have a matching between the equation of angular part and the Legendre differential equation, right? So there we didn't need to worry about doing further work in finding, or let's say finding any mathematical method to solve this equation, right? So for the angular part it was easy, but for the radial part, as you see, there is basically one in the potential, there is one over r term, and there is another 1 over r square term, right? So it actually complicates the problem. So we don't have a very easy way to find the solution. You understood what I'm saying?
Yes, sir.
Okay, so let me, I think, write it down here. So let's see. Where am I here? Okay. So get a new slide. Okay. So let's first see basically. Let's say if I have an equation like, I don't know, like d2u dr square will be some coefficient times u. Okay. So we know what will be the form of solution, right? Or let's say if we have an equation d2u dr square will be some minus some coefficient times u, we will also know what will be the form of solution, right? So
Yes, sir.
these are kind of standard form of equations of second order differential equations which you know the solution. Okay, but here unfortunately what we are having is that we have some second order differential equation d2u dr2 plus, let's say. Okay, and then in the potential we have a 1 by r term minus, I think, and then plus 1 over r square term, and then something will be e times this. Okay, so we don't have a necessary exact solution for this thing, right? So what we are doing is that we are trying to find out the solution by looking at different limits. Okay, so one way of looking at it is basically, so first what we did is that we actually, where is it? Basically, let me see here. Okay, so the first thing what we did is that we did a change of variable here. Okay, that is ur will be r times small r times capital R. Okay, and from there actually we have arrived at this equation. Where is it? I think this expression. Okay, d2u d rho to rho is this is basically n here. So we have not taken any assumptions so far. Okay, so this is the expression we ended up here. Equation 31. Now, what are we trying to do here is that we are just trying to find out that what sort of solutions are physically possible in this system and which are not physically possible. Okay, so we are looking at the physical description of the system and different limits. Okay, so the first one what we did is that we consider infinite distance. Okay, that is rho goes to infinity, and there we have seen that this e to the power rho term cannot be present there. Okay, on the other hand, what we did is that we consider rho goes to 0 term, and we've seen that this rho to the power minus L term cannot be present there. Okay, and at the same time, we have seen which terms can stay. That is rho times rho to the power L plus 1 can stay, and e to the power minus rho can stay. Okay, so now if I want to take the next step, then what I have to do is that I have to construct an wave function where I know that how it will behave in the asymptotic limits. Okay, so when r goes to 0, then what will be the functional form of wave function? When r goes to infinity, what will be the functional form of wave function? So if I know these two, then basically the final wave function will be a product of these two terms and another term which is a function of rho or r. Is it clear?
Yes, sir.
No, is this clear? Tell me.
Yes, sir.
Okay, okay. Okay, so any other question? Okay, so if not, then I will finish it here today.